Okay, so the first of our Extension 2 topics, the unfortunate named complex numbers. I say unfortunate. I mean, they could have called them anything. They decided to call them complex, and the word complex sends off little triggers in our heads, and we think, oh, complex, must be hard, complex. Right? It's the same as, I think I mentioned this the other day, is when they call them imaginary numbers. So people went, oh, they don't exist because they're imaginary. They're just names they gave them. They do exist. Complex does not mean this is hard, things like that. It comes about because we want to solve a problem, much like anything that happens in mathematics, really. And that's what we do in maths. We're trying to solve things. And when we hit a problem, if we can't come up with a way of solving it, we'll create some sort of new way of doing it. Classic example of that is, we used to say things in primary school. If we'd said, what's 10 minus 12? And the answer then was, I can't do it. Yeah? 10 minus 12? Nah. And so how we solved that problem? We introduced negative numbers, and then, oh, what do you know? We can do it. What's 8 divided by 3? 3 doesn't go into 8. Can't do that. All right? And so then the whole idea of fractions and not just whole numbers. So complex numbers, it was another solution to a problem. And it was solving this equation, x squared plus 1 is equal to 0. Well, okay, it's a quadratic. We know how to solve that. Move it to the other side, and we have this problem. We got no solutions using the numbers that we knew. So they said, well, okay, let's create a new number, and then we can solve the problem. So in order to solve it, we define this new number, I, the square root of negative 1. Or another way of saying it, I squared is negative 1. I just stands for imaginary number. Okay? So because we now know what the square root of negative 1 is, we can simplify the square root of negative numbers. So now I can go back to my problem and go, well, x is plus or minus the square root of negative 1. Oh, so it's plus or minus I, because I now know what the square root of negative 1 is. I have a solution to the problem. Okay? So, all right, we now need some definitions, how we deal with this new class of numbers. So all complex numbers can be written. Common letter we use is Z. W is another fairly common one, but just Z. And we write it as x plus IY. And what we say is all numbers have a real part and an imaginary part. So all the numbers that you've been dealing with all your life are still complex numbers. It's just that their imaginary part was equal to 0. So define them. So a real part and an imaginary part. So the real part would be the x, and the imaginary part would be the y. Now that's the first thing to point out. These are real numbers, x and y. So if I say to you, what's the imaginary part, you don't say it's IY. The I is telling you it's imaginary. They want to know the actual real number that's associated with that. So just the y. So if I have 3 plus 5i, the real part is 3. Well, that's the obvious one. Imaginary part, we don't say 5i. We say, oh, it's just 5. 5's the imaginary part. So if the real part is equal to 0, then that's what we call a pure imaginary number. It has no real part to it. Okay, so that's called a pure imaginary number. So examples, the square root of 3i minus 6i. Anything I would be a pure imaginary number. And if the imaginary part is 0, as I say, that's what we're used to dealing with, and that's what we've been calling real numbers. 3/4 would be an example. Pi would be an example. E is an example. -4. We can think of lots of examples of real numbers. Now, every complex number has a complex conjugate. Now, we've seen that word before, conjugate. Where? Yeah. So when we were rationalising. And the reason for that is, if you think about it, a complex number is a surd, because I is the square root of -1. So a complex conjugate is just like in surds, you have a conjugate. You just change the sign. So the conjugate, and one of the common symbols we see is just with a horizontal bar above the Z. So that represents the conjugate of Z, and that would be x minus IY. We just change the sign on the surd, just like we did when we were rationalising denominators. So if I have minus 2 minus root 7i, its conjugate is minus 2 plus root 7i. Right, so here's the picture of complex numbers, which is, of course, as you now know, is every single number that you've ever been dealing with, plus these new ones as well. So how do our numbers fit together? What you've been dealing with so far are real numbers. So that's where y is equal to 0. But now we have these imaginary numbers where y does not equal 0. You'll notice there's no point of intersection between the real numbers and the imaginary numbers. So rational numbers sit inside the real numbers. Remember, they're the ones that can be written as fractions. Then, of course, there's the irrational numbers, the ones that can't be written as fractions. So again, there's no point of intersection between those two. Then inside the rationals, well, when I say fractions, I mean ones that are written as fractions. I don't mean over 1. Obviously, every number can be written as a fraction. So I'm talking about what we traditionally think of as fractions, where we have a numerator and a denominator and it can't be simplified down. But then we have the integers, so they're the ones that would be over 1, if you like, so the whole numbers. And inside the integers, we have the natural numbers. Oh, now we're going back a long way for definition. Natural numbers, what are they? We know they're integers because they're inside the integers. What particular integers are the natural numbers? Positive doesn't include 0. Another name for natural numbers is, of course, the counting numbers. And so if I was to say to you, start counting, you wouldn't go 0, 1, 2, 3, 4. You'd start at 1. Okay. Speaking of 0, there's 0 sitting by itself. It's that really weird number. Should it be there? Well, yes, its imaginary part is 0, so I suppose it's in the right spot. And then, overlapping all that, I suppose it should overlap the natural. Oh, no, it doesn't overlap the naturals, does it? They're the counting numbers, so that is right. Negatives, and you can have negative irrational numbers, you can have negative fractions, you can have negative integers. Okay, over in the imaginary numbers. The imaginary numbers don't have as many things. Really, it just has imaginary numbers, pure imaginary numbers. So the pure imaginary numbers are the ones where the real part was equal to 0. So obviously that sits inside the imaginary numbers. But other than that, that's pretty much it as far as imaginary numbers go. Note, you cannot order imaginary numbers. You cannot order them because you can't place them on the number line. Right? Definition of the imaginary number is that y does not equal 0. So the real part, the imaginary part exists. Now, when we see a pictorial view of this, you'll understand why. But all the imaginary numbers sit either above or below the number line, if you like. They're sort of out in space. So you can't order them. Because who's to say? Is 2i bigger than minus 2i? You want to say no, because of the negative. But what about this one then? 2 plus 3i, 3 plus 2i. Which one's bigger? Now we've got a problem, because, well, hang on. They're using the same numbers. So you just can't order the imaginary numbers. How do we deal with them? Basic operations. Well, if you think of them as a surd, you already know how to deal with them. Or you can think of them as algebra as well, because you can think of I like a pronumeral. So I is a surd, operation with complex numbers, same as a surd. So we want to add them, the real part with the real part, the imaginary part with the imaginary part. Remember, the two sets, imaginary numbers, real numbers, there's no point of intersection. So I can't go and get an imaginary number and add it to a real number and get an answer. So I can only add the real with the real and the imaginary with the imaginary. So just like algebra, I'd end up with an answer for the real part and an answer for the imaginary part. So minus 4 minus I. And same with subtraction, of course. So just like algebra, there it is, 12 minus 5i. Multiplication becomes like a binomial expansion. So first outside, inside last, but This is where it becomes a little bit different now, because every time we see I squared, the number has now become real, because I squared is equal to -1. So we don't leave it as minus 6I squared. That becomes plus 6. Okay? And after a while, you'll get into the habit of not even writing minus 6I squared down. You'll just automatically go, oh, well, minus 3I times 2I is 6. And tidying that up, there's our final answer. Minus 26 plus 32I. Well, division, we now call realising the denominator. Exactly the same as rationalising the denominator. We're going to multiply by its conjugate. But the difference is we want to turn the denominator into a real number. Not necessarily a rational number, but a real number. So we'll multiply it by the conjugate, expanding out. Now, at the bottom of the fraction, you've got conjugates. When we're dealing with real numbers and we multiply by conjugates, we get the difference of 2 squares. When we're dealing with complex numbers, we get the sum of 2 squares. Because you're going to have the I squared there in that second part. So instead of going difference of 2 squares, A squared minus B squared, you're now going A squared minus I squared B squared, but I squared is -1, so you get A squared plus B squared. Got to be real careful with that, because it's so easy to go 64 minus 4 instead of plus 4, because we're just so used to doing that when we're playing with surds. So what does that tidy up to be? There we go. Minus 19 on 34 plus 8 on 34i. Now, if you remember with surds, there's no big deal if you leave a surd in the denominator. I mean, if I was to say to you, what's the exact value of sine 45, most people would say 1 on root 2. They wouldn't worry about rationalising the denominator. The difference with these is we must have a real denominator. We cannot compare them unless the denominators are real. So we always make a real denominator. So some basics of playing around with conjugates. If you want to find conjugates of numbers, the order does not matter. What this is saying is you could add the two numbers together first, then find its conjugate, or you could find the conjugates, then add them. So it doesn't matter which way around you do it. Same with multiplication, same with division. As I was saying, if you multiply a number with its conjugate, you no longer get the difference of 2 squares, you now get the sum of 2 squares. So you get x squared plus y squared. And a quick way of finding the reciprocal of a complex number, it turns out to be the conjugate over z conjugate. Because have a look, all I've done is I've multiplied top and bottom by the conjugate. If I think of it that way, it's very quick, because all I've got to do then is write the conjugate on top and then the sum of 2 squares on the bottom, and I've got the reciprocal of the complex number. So if I wanted to find the reciprocal of 1 on 4 minus 3i, then I know, oh, that's going to be 4 plus 3i on the top, the conjugate. Sum of 2 squares, 16 plus 9. So there's my answer. 4 on 25 plus 3 on 25i. So that's how we manipulate them, just like surds or just like algebra. So how do we solve equations? Again, the real and the imaginary can't mix. So this is a bit like, you remember when we did quadratic identities and we said the coefficient of x squared must equal the coefficient of x squared. Coefficient of x must equal the coefficient of x. It's the same sort of idea. So when we have an equation, we're saying the real part will equal the real part. The imaginary part will equal the imaginary part, because they can't mix. So if two complex numbers are equal, the real parts are equal, the imaginary parts are equal. So to put that in a more formal way, I suppose, if A1 plus B1i is the same as A2 plus B2i, then the only possibility for this is that A1 is equal to A2 and B1 is equal to B2. So the real and the imaginaries don't mix. Okay, we got to find x and y. Now, a couple of ways I could do it, I suppose. I could divide by the 2 plus 3i. And then I know whatever I get on the right-hand side, the real part will equal the real part, the imaginary part will equal the imaginary part. Or I could expand out the left-hand side and group. Which way did I go? I've gone the expanded out way. So on the left-hand side, when I expand this out, again, being careful, 3i times iy is minus 3y because of the I squared. So the real part, 2x minus 3y is 4. The imaginary part, 3x plus 2y is minus 2. And I solve those simultaneous equations. And there, I get x equals 2 on 13. And so from there, y is 16 on 13. I wonder, would it have been quicker to divide both sides by the 2 plus 3i and then possibly. But just like other equations, there are different ways of solving a problem. Simultaneous equations. For some reason, some people look at these and think, oh my God, simultaneous equations. But the idea doesn't change. The rules of maths have not changed. If I wanted to solve simultaneous equations, I want the coefficient to be equal, and then I can eliminate. So the coefficient of either the z or the w, I want to make the same. The idea doesn't change. So I'm going to make the coefficient of w the same. So in the bottom one, I just multiply everything by 2. And the coefficient is 2iw for both of them. Do a subtraction, and I've actually subtracted up just to keep the z's positive. So 3z is 2 plus 5i. I have what z is. What would I then do in a normal simultaneous equation? Oh, well, I'd go and substitute in and find the other one. That's exactly what I do. Z is 2/3 plus 5/3 I. Substitute it back in. I've chosen the top one to substitute back in. Okay, so I've got 2iw is 10/3 plus 4/3 I. So I have to divide by 2i. So I get 10 on 6i plus 4 on 6. Now, be careful, I've swapped it around. I'm not saying 10 on 6i is 2/3 here. I just always put the real part first. So 4 over 6 is 2/3. 10 over 6 is, of course, 5/3. If you've got I on the bottom and you want to put I on the top, then you put I on the top and you just change the sign. Because what are you doing? You're multiplying by the conjugate. What's the conjugate I? Minus I. So it has the effect of just changing. You can put the I on the top and change the sign. You just got the I on the bottom. All right. Now, Patel is the handout that I've given you. That, of course, is our sort of main textbook. And then Cambridge.